So, welcome to the 14th lecture of combinatorics. In the last class we were discussing the Stirling's formula for factorial. So, this is when we ask how big is these parameters NCR, NPR, etc. So, one tool we can use to kind of approximately know how much these quantities are is the Stirling's formula. So, this is n factorial is equal to n by e to the power n root of 2 pi n. So, I am taking it is not Feller's formula. So, I am taking this whatever I am discussing is taken from William Feller's An Introduction to Probability Theory and its Applications. That is why I just wrote it there. Now, in the last class I was telling I will kind of give the starting of the proof. So, of course, I can just skip the proof because it has nothing much to do with combinatorics, but still to make sure that the curious student kind of understands where it is coming from. So, we will like begin the proof and then drop it, because then I will give. So, because Feller's book has the complete proof, the student can go and check it there. So, this is the way it goes about. So, we want to show that n factorial is approximately equal to root of 2 pi into n to the power n plus half e to the power minus n. This is what. So, in other words, we want to show that, as we discussed in the last class, the ratio of these two quantities LHS by RHS will tend to 1 as n tends to infinity. So, the trick is this, for how will you guess this part is the first question, right. So, we work with, so we will rather work with log of n factorial, and we want to show that it is approximately equal to the, so it is tending to the log of this thing, so that this formula will come, that is approximately some the n log of this root 2 pi and then into n plus half into log n, yeah. Sorry, when you say log, so this will be plus, okay, plus and minus n. This is what we want to show, right. This is what we will. So, in other words, we will be working with log rather than directly. So, rather than working directly with this stuff, we will work rather directly rather with log, right. So, I just took the logarithm of this thing. This is what I am going to show. So, then, so this is the way we are going to do. So, we notice that when you integrate log x dx, right. So, it is something like x log x minus x plus c. So, just I mean you can try differentiating on this side and we will see that this is coming out. So, therefore, so what we are going to do is, so of course I won't show the integration as such, but you just remember this thing, and then we notice that, so okay, I can try it from 0 to 1 log, so if I write 0 to 1 log x dx, so this is definitely less than log 1, because this is a range of 0 to 1 and this curve log x is integrated, and then log 1 is the biggest in this thing. It's an increasing function, monotonously increasing from 0 to 1, and then you see this unit. So, therefore, this portion is going to be strictly less than log 1. Of course, you have to go back to your calculus course and then remember all these things, and this is less than equal to, definitely if you go from 1 to 2 log x, right, this is what is happening, dx, right. Now, we can do it from 0 to 1, then so we can do it from 1 to 2 now here. So this is log x dx is less than log 1, log 2 of course, because you know this is the higher range. So log 2, because the highest value into 1 is what we are taking here. So because this is 1, so integration is happening from 1 to 2, that is the difference is 1. So the biggest value into 1 will be an upbound for that, right, less than, so 2 to 3 log x dx. Now we can keep on writing it till say n minus 1 to n log x dx. This is less than log n, this is less than n to n plus 1 log x dx, right. Now we sum up all these things, starting this one, this one, this one. So this entire, this below before whatever this less than equal to sign was written, if we sum up, what do we get? We are actually integrating from 0 to n, right. We started from 0 to 1, 1 to 2, 2 to 3, like that, n minus 1 to n finally. So 0 to n it is log x dx is what is coming here. Here what is happening is you started with log 1, so that will be added log 2 plus like that log n will be like, this is less than equal to something is what is. So here what is this? So you remember here it is log 1, then it is log 2, next will be log 3 and all the way log n. So we are adding up all of them. So this quantity will turn out to be, see, log 1 into log 1 plus log 2 plus up to log n. So when you take all of them inside log, so or when you combine them, that happens log of 1 into 2 into up to n, right. So this can be rewritten as log of n factorial, right, log of n factorial, because when you add up all those logs, and if you just want one log, what happens is this, we take the product, right. So this is less than equal to integral of 1 to n plus 1, right, log x dx. Now we know, we have seen that log x dx, when we integrate we will get this stuff. So we can substitute the limits in that, right, 0 to n here. So we substitute in x log x minus x, the 0 to n, what will we get? So we will get n log n, right, minus n we will get, right. And when you substitute in this x log x minus x, n plus 1 is substituted, we will get n plus 1 into log of n plus 1 minus n plus 1 will come, right, minus n plus 1. So we can write it as minus n plus 1, right. So now you know you are, so this is the upper, see what was this n factorial was in between this and this is what we have seen, right. So this was less than equal to, this was less, this is the way it was written, remember. So this quantity is a lower quantity compared to log n factorial, and this quantity is a bigger quantity compared to log n factorial. So this log n factorial will be sandwiched in between these two quantities, n log n minus n and n plus n, n plus 1 log n plus 1 minus n plus 1. So we can kind of think that it is in the middle, somewhere in the middle. For instance, if I add up these two things, this one and this thing, and try to divide, so this will be n log n. Let's say make some minor approximations. This log n plus 1 we will just consider as log n only, that is n plus n. So it will become n log n plus n plus 1 log n. Yeah, this was log n plus 1, remember, but we are just putting log n here. and then here a minus n, and then here a minus n, and so plus 1, right. So, this is what will come, right. So, sorry, this here I have written a wrong thing, because n plus 1. So, this is 1 2. So, this limit was 1 to n plus 1. So, you put n plus 1 log n plus 1. So, you have to minus this. This is not from 0 to, right. So, minus something here, right. So, sorry, minus something here. What is that? When you put 1 here for x, this is 1 into log 1, that will be 0. So, there will be a minus of minus 1. Right. So, here this is minus n plus 1, and then here a minus of minus 1, that is a plus 1 will come. So, when you n plus 1 log n plus 1, this minus 1 and this one, this is minus 1 and this one will cancel. So, finally, what would remain here is n plus 1 log n plus 1 minus n, because see this I just forgot in the earlier when I discussed it before, I just forgot that there was a 1 here. So, there will be contribution from here, that was why minus of n plus 1 was coming. So, now I corrected it, it is just this. So, therefore, that is just minus n, right. So, now if you take half of this entire quantity, so see here is the only place where I just changed, for convenience sake I am just, because this is not part of the proof, we are just trying to see approximately where is the middle of these bounds. There is a lower bound, there is an upper bound. So, like what is the average of those two bounds, so that we can compare that sandwich quantity, namely log of n factorial with that, right. So, instead of, because to make it, so if I add n log n and n plus 1 log n plus 1, we will not be able to simplify. So, we will just n plus 1, instead of n plus 1 I just put log n. So, this will become half of log n. So, this is just n log n, right, and here is a half log n, because half into 1 log n, that is n plus, I can write n plus half log n, right, and then here minus 2 minus n by 2 is minus n, right, minus n, 2 minus n is minus n. Minus n will be minus n. So, what we have seen is, because log n factorial is sandwiched between these two quantities n log n minus n and n plus 1 log n plus 1 minus n, right. So, approximately so we have done a calculation, just putting, instead of n plus 1 I just put log n, approximately the midpoint of from here to the average of this thing, right, middle, if you take this plus this by half, if you get something like n plus half log n minus n. So, we think that maybe log n factorial will be very near to that, right, it will be very near to that is we will think. So, we with that intuition we try to evaluate the difference between these two, log n factorial minus n plus half log n minus half. That means we are interested in this quantity log n factorial minus n plus half into log n plus n, right. So, this overall minus. So, let us define this as some sequence dn. So, we will have for n equal to 1 d1, then n equal to 2 d2 and so on, right. So, we can write certain numbers, right, and so the question is, as n tends to infinity, what happens to this sequence dn. So, the aim is to show what we have to show is dn tends to some constant c. If dn tends to some constant c, then what will happen is this quantity will tend to a constant c, right. This will tend to a constant c. Now, we can rearrange, and that will say that log n factorial is equal to c plus n plus half into log n minus n as n tends to infinity. Now, you take the e power LHS equal to e power RHS. So, that will tell us n factorial. Yeah, if you do that, e power LHS equal to e power RHS in this following equation, that means log n factorial equal to c c plus, right, c plus n plus half log n minus n, right. So, now if you take e power LHS, so this will be n factorial, this will be equal to e power c into n raised to n plus half into e to the power minus n. The only thing is, what is this, right. This requires a little more work, and then it will be shown that this will be 2 pi root 2 pi, right. So, this I will not do. So, this is, and again, so yeah, of course, proving that actually dn tends to something requires a little bit of effort. I can do it, but to save time I will skip it because of course it has nothing much to do with combinatorics. I just gave this much to give the student feeling of where it is coming from, maybe how one can move about it. If he is really curious about the complete proof, he can probably read it from Feller's book, which I have mentioned before, right. So, it is not really important to know the proof. More important is to know the formula well, and to be able to apply it when the situation comes. Now, I will just mention that we wrote it approximately equal to. We can make it a little more clearer by saying that n factorial is equal to n by e raised to n. This is here n to the power n, e to the power minus n is already there. That n to the power half we have taken inside this root 2 pi n, right. That root n is coming here. So, 2 pi n, but other than that, that approximately, that is e to the power alpha n we have captured, that the remaining, the difference will be captured in the e to the power alpha n, where alpha n is some quantity. Again, we do not know exactly what it is, but we are telling again it is going to be in between 1 by 12 n plus 1 and 1 by 12 n. So, this is quite a small quantity. As n tends to infinity, e to the, it is going to be e to the power 0, it will tend to 0, but so therefore, whatever we previously did is correct, but even for large enough n, right, this is if you take one of these value, either 1 by 12 n, we will get an upper bound here. You can put e to the power 1 by 12 n here for this thing. This will be n factorial less than this thing. It will be bigger, but only slightly bigger, because instead of putting 1 by 12 n, if you had put 1 by 12 n plus 1, you will get a lower bound also. You can imagine that yeah. So, you are thinking that some very large number, say, or maybe even 100 if you put, right. So, this quantity into e to the power 1 by 1200, right, will be an upper bound, while this quantity, that is n by e to the power n into root of 2 pi n into e to the power, so when n is equal to 100 there, okay, of course, into the power e to the power 1 by 1201 will be a lower bound. So, it is not very far, right, it is quite this thing. We can see in most of the cases we can just say that there exists a constant C1 who is sufficiently large n, that this n factorial is in between n by e to the power n root 2 pi n into that constant 1 and the same thing into constant 2, right. So, in between some constant times this means okay, in the earlier what we have written approximately in the earlier, right, this quantity into some constant 1 and this quantity into some constant 2, where constant 2 is slightly bigger than constant 1. It is very close constants. So, that is n factorial will be sandwiched in between that, right. That is what it means. Most of the time we can just use it that way, right. So, I think this much discussion is enough for this thing. You will, for instance, if you want some more like ready made formulas for say quantities like n choose n alpha, where alpha is a constant alpha, say alpha less than 1 of course is a constant, is a real number, is a real constant. Then so you will get some good formula. So, by applying the Stirling formula you can derive that. You can try doing this. So, but in Stas's Jukna's extremal combinatorics you can see some exercises in the first Jukna. Okay. So, I have mentioned this book in the first lecture. This is called extremal combinatorics. So, you can get some exercises where you can, anyway you have to, that is only exercises, you have to work out, right, and it is not very difficult. You just substitute the formula and then manipulate, and also some partial sums, n choose 0 plus n choose 1, say up to certain quantity if you sum n choose k, what can you tell about some upper bounds, right. This kind of questions are dealt with in some of the exercises there in Jukna's book. So, yes, so we can, you can go and read it. So, in that so now we will move on from this thing. The next topic we want to consider is the following. Is again some slightly special topic, maybe most of the combinatorics courses may not take it. So, starting from here, maybe couple of classes I will deal with this thing. This is, most of this material is taken from the book Concrete Mathematics. Concrete, oh shit. So, this is taken from the book Concrete Mathematics. So, stuck. This is again. Yeah, Concrete Mathematics. So, we can take it from the book Concrete Mathematics. It's a famous book by Nuth Graham Patashnik, Nuth Graham Patashnik. So, yeah, so of course there are a lot of material in that book. There are a lot of material in that of this type in the book. The book chapter number is 5. This is chapter number 5. The kind of material I am talking about. I have just taken some of the initial material to give a feel of that, right. So, the rest of the things, if you are interested, you can read. If the student is interested, you can read from that book. So, of course, this is slightly different kind of treatment. So, so this is what. Yeah. So, this is what we are going to do. So, first let us mention about falling factorial and rising factorial. So, we haven't mentioned this up to now, right. So, The falling factorial means, suppose you are given a number r. So, this can be a real number, it can be a complex number. So, the falling factorial is written like this, falling, r k falling, k being a, say, suppose let us say it is a positive integer, we will just consider k to be a positive integer. R can be a complex number, a real number, whatever. And then what is this r falling factorial? It is this one, r into r minus 1 into r minus 2 into, see, r minus k plus 1. This is the falling factorial, right. So, for example, let r equal to 5. So, what is r 3? So, that is 5 into 4 into 3. We just collect 3 of them downward, right. It is falling. Similarly, suppose r equal to minus 3, then what is r raised to 4 factorial, for falling, that will be minus 3 into minus 4 into minus 5 into minus 6. What we have done is, starting from minus 3 we go down, minus 4, minus 5, minus 6, because we need 4 of them, right. And similarly we can ask, what is, suppose r equal to half, what is r falling factorial? 3. This will be half into half minus 1 into half minus 2, right. So, 1, 2, 3 terms are written starting from there. So, this is the falling factorial, r 3 falling factorial, 3 r to the falling power 3, right. So, it is a falling factorial powers, that is the way we can call it, falling factorial powers, r to the power 3. So, r to the falling power 3. So, then we can, for instance, we will have certain doubts now. So, one thing is, like whatever we have seen up to now for combinatorial, something like NPK kind of thing. So, this is essentially NK falling, right. So, because we were seeing that this is n into n minus 1 into n minus 2 into, so n minus k plus 1. So, k terms are written downward, right. Not that if k was, see, as long as k is less than equal to n, this will make sense, because this will go from n to 1. So, for instance, n to some number which is still bigger than 1. So, that is okay. So, for instance, n falling factorial will be n factorial itself, right. So, now what will be n plus 1 falling factorial? So, then what happens is, here we will write n minus 1. So, n minus 1, then n minus 2, and all the way we reach 1. Then we also have to write 0. So, this will become 0. So, anything bigger than n here in the falling power, so that will make it 0, right. So, similarly, so n 1 falling will be n itself. Now, what is n 0 falling? N 0 falling will be defined as 1. So, this is one thing you should remember. So, r 0 falling is defined as 1, and I guess we can define for negative numbers, if you want, it can be defined as 0. So, though we will not be using it most of the time. So, we will be most of the time considering only k greater than equal to 0 and non-negative integers, but if at all, so we can also define for negative numbers, it is 0. But this is important, because this is by definition, this is r or 0 falling is 1. Similarly, we have a rising factorial also, rising factorial power r. So, it is written like this, instead of a bar below we rise above. So, r into r plus 1 into, so instead of r minus 1 we will write r into r plus 1 into r plus 2 into all the way r plus k minus 1. This is what rising factorial power, right. So, this is the definition, corresponding definition for all these things, whatever we whatever examples we gave before for rising factorial is essentially falling factorial. So, we can also try with rising factorial. So, there is not much difference. So, maybe one of the special cases we can mention n what is n1 rising, that is again n, there is no difference, n rising and falling, when you just use 1 it is going to be. So, for 0 we can again define it as 1 and then the 1 n rising is 1 into 2 into 3 into up to n. So, that is n factorial. So, remember the n falling is equal to n factorial, that is equal to 1 rising n, right. This kind of things you can remember. Okay, these are two concepts, rising factorial and falling factorial. So, and then we can remember that n choose r. So, n choose k, we say n choose k, this was n k falling factorial divided by k factorial, right, using the falling factorial notation, because this is actually n into n minus 1 into up to n minus k plus 1 divided by k factorial. Good. So, this is, now again we go to the next thing. So, yeah, the next thing is to generalize the notion of the combinatorial coefficient r choose k, right. R choose k is now generalized. We just write it as r k falling factorial divided by k factorial. See, the difference is, up to now we were always insisting that this is called upper index of case, this upper index, this is upper index and this is called a lower index. So, we are always insisting that this upper index has to be a non-negative integer, right. We are not allowing negative integers, we are not allowing real numbers, we are not allowing complex numbers, nothing, only non-negative integers. Now, we are saying that we drop all the restrictions on r, you can use any complex number there. That is one important thing in the generalization. And then second, here we allow any integer, in the lower index we allow any integer, this is any complex number, here we allow any integer. So, even negative integers. So, though you will, so the way we define it is, so we just say that when this is for k greater than equal to 0, so integer when k is integer and greater than equal to 0, we will define like this. For instance, here the trouble is that if you define like this for k negative, then we have to say what is a minus 3 factorial, minus 4 factorial. So, negative numbers factorial, what is that? That we do not know, right. So, we insist that k is an integer and k is greater than equal to 0 when we define this thing r k falling factorial and then divided by k factorial. Otherwise, we will just define it as 0 for k less than 0. If this is an integer and then less than 0, then we will just define it as 0. This is the way we have defined, we have generalized it, right. So, the upper index is fully generalized to any complex number, the lower index is generalized from being just non-negative integers to any integer, but just that when it is a negative integer we will always define it as 0, and then when it is a non-negative integer, upper index is r falling factorial, upper is actually this is a ratio where numerator is r falling factorial k r to the power k falling factor r to the k falling factorial power, and then divided by k factorial, right. And then so of course this is well defined, right. So now of course one can ask why are we restricting k to be integers. So the argument in concrete mathematics is the book is that it is application wise, as far as the applications are concerned, this much generalization is usually sufficient, but they have given further generalization, but the interested student can read it from the book Concrete Mathematics. So we just stick with this much generalization and go ahead. So the point here is to say that, so if I generalize it, there are no more combinatorial interpretation for these things, right. So R is a complex number, and so there is nothing like we cannot define R choose K as the number of ways of taking K subsets of an R element set, because there is no R element set now. So it does not make sense to think like that. So this is just defined that way, and just that when R is a non-negative integer, it coincides with that counting interpretation, right. It is the same, right, whatever the number of ways of selecting K things out of R things, right. So so we, if you want this all those identities we proved, we cannot just take them, because we always proved assuming that there is a combinatorial interpretation, there is a counting argument therein. So then the counting argument works only when R is non-negative integer, and right. So therefore we will have to redo some of the identities if we have to work with these things, is this generalized stuff, right. So we will, of course one can ask why do you want to generalize. The reason is that there are a lot of applications. So there are of course because as we will see soon, even the binomial theorem can be generalized to 1 plus x raised to r. So we were seeing 1 plus x raised to n, where n is a non-negative integer, but now here we can use, instead of n we can put any r, where r is a complex number or real number. So now this will have the same kind of expansion, just that it will be now a like infinite sum. So r choose k into x raised to k, something like this, right. So or maybe we could have always written as x plus y raised to, right. So that will give us y raised to right. So we see this is the general format 1 plus x raised to, we will see how we can get x plus y raised to r from this thing. So I will just postpone the discussion to the correct time, right. So this is so the point is we can generalize it for overall k. So therefore so in the sense this is going to be very useful in many cases. For instance, you could have put, instead of r you can put a -1 here and then work with it, right. So therefore the -1 you can put r equal to -1. So all these things will make -1 to the choose k will make sense, right. For every k you can evaluate this stuff and then write an infinite formula for that. So that expansion will turn out to be useful, right. So therefore if since it comes it becomes important in many other cases. So in counting probably it doesn't come so often. So we should be aware of such a generalization when because we may encounter it somewhere, right. So therefore we will have a quick discussion of it. So now we will see what all things we have to be careful about when dealing with this stuff, right. This is what the intention of this discussion. So nothing serious, but just in passing we will consider some of the most important identities and see what difference is there. For instance, the symmetry identity may be one of the most important ones. So that is n choose k equal to important and simple, n choose n minus k. We have seen that there is a combinatorial interpretation for that. You are taking k things out of n things. So that means we are leaving out n minus k things. So therefore the number of ways of selecting k things out of n things will be equal to the number of ways of selecting n minus k things out of n things. This is how we prove it. But then we assume that there are n things, that means n is a non-negative integer, right. Out of that we have to select k things. Now but now we want to show this one, r choose k equal to r choose k minus 1. Now we see what all restrictions are there. Sorry, r choose r minus k. So here our generalization will not make too much sense, because though we told r can be any arbitrary complex number. So this is an integer, right. This has to be integer to make sense, r choose k. So but then r minus k, if r was not an integer, r minus k won't be an integer. So this won't make sense at all, the second part, right, the RHS won't make sense of. So automatically this formula put the so this identity put the constraint that r is also an integer, right. Then only we can even talk about this identity. So though we have generalized, that is not going to the formula is, the identity is not going to generalize. Okay, fine, let us still keep r integer. Is it possible that I can work with all possible integers? The point is that even that is not true, right, because even that is not true, because see, you can see that, yeah. So for instance, if we take minus 1, right. So minus 1 choose 0, you can try. So minus 1 choose 0. So we need minus 1 choose minus 1 minus 0. This is what we want. Is this correct? This is what we are asking, right. But then this is what, minus 1 choose minus 1. So is it 1? So we always see n choose n, yeah, we may tend to say that it is 1, but then this is not correct when this lower index is minus, right. That is the way we have defined. We go back to the definition, we see that if k is less than 0, irrespective of whatever is the value of r, we defined it as 0. So this is so this is not true when, for instance, n equal to minus 1. So minus 1 choose minus 1 is 0, not 1. So this is going to be 0, right. But this one is 1, right, because what? So this is minus 1 to the power 0 falling factorial, which is 1 divided by 0 factorial, right. This is 1 by 1 is 1. So here it is 1 and there is a 0. So this is not correct. So our generalization is not working, even with the assumption that r is an integer, right. When I took r equal to negative 1, it is not working. So with k equal to 0 of case. So we can try with k some other negative number, so 0 and some negative number we can say r choose. So let r is some negative integer, something like minus 10. So minus okay, minus 1 we can say, minus 1, say minus some negative integer, let us see, k is a negative integer, right. So, because if this k is a negative integer, so we want to get minus 1 choose minus 1 minus k, right. This being a negative integer, maybe we can put a value there for this, just for the sake, let us say this is minus 10. So, minus 1 choose minus 10, but we know our rule says when k is less than 0, irrespective of the value of r, this value is going to be 0. Here what is happening? Here it is minus of minus 10, that means 10 minus 1, it will become 9 then, right. Minus 1 choose 9, but there it is there is a value, because what will it do? So that it will just calculate minus 1 into minus 2 into minus 3 into, like that, it will go downward 9 times, right. Minus 1 minus minus 1 minus, okay, yeah, minus 1, yeah. So what I am saying is 0, yeah. So what I am saying is, yeah, this minus 1 choose 9, right. Minus minus 1 yeah, minus 1 choose 9 will be equal to minus 1 into minus 2 into, so up to minus 9 plus 1, right. So 9, sorry, minus 9 of them, right. So divided by 9 factorial. So this will be some minus 1 raised to 9 into 9 factorial by 9 factorial. This is the way it will come. So therefore this is going to be a non-zero quantity, but on the other side we always get a negative quantity. So this is, you can easily, there is above, putting minus 1 above is not very important. If you had put something else, say minus r, some negative quantity here, negative number here, and then you have tried it with some that r choose k. If k is negative anyway, this side is 0, and then the comparison is whether it is equal to r choose k minus this one. So this already negative quantity, negative minus negative quantity, this is a positive quantity, and whatever it is, this r falling factorial is defined, and because it is a negative number, it will it's anyway it won't become 0, and then because a negative number, it will minus minus minus, it is going downward, right, divided by r minus k factorial. See, r is a negative number, this is also a negative number, right. So yeah, k minus, right. So that is, so therefore in many cases, so you will see that it is not going to work, but on the other hand, when we take r is, so once we take r is positive, this issue is not there, because this will work, because you know r is positive means positive integer, positive or 0, non-negative integers. So we know that it is already working. So this is because we know that r choose r minus k was true just for all positive integers, because by the counting argument we had already shown that. But in the case that k is in between 0 and r, this we already know. But on the other hand, if k was less than 0, definitely this will be negative, and this will be r minus a negative number, this will be r choose something bigger than r, so that will be again 0, right, because the falling factor will become 0, in the numerator things will become 0. Now if k was greater than r, so this quantity is anyway 0, because here r choose something bigger than r, and r falling factorial k will become 0, then definitely it will become 0. Here r minus k is going to be negative, because it is a negative number, by definition it is going to be 0. So, 0 equal to 0. So, that is not a problem. Once r is a non-negative integer, whether k is positive or negative, we see that this symmetry identity is working, right. So, this was a discussion to bring out the subtleties. So, that means we have to be careful that just because we proved the identity in the combinatorial setting, that means n was a positive, r was a non-negative integer, it does not mean that it works in the generalization. It need not work, right. So, that as we have seen in this example, the formula need not even make sense, right. So, we have to carefully reanalyze it, but of course, whatever we have already done will help us, because at least as we have seen in the proof in the later part, we could use the combinatorial proof for most of the non-trivial cases. Other things were trivial, just noting that both sides are 0, it was easy in fact, right. So, we will take another example where it works. This probably we have not seen before. Yeah. So, this is called absorption identity. This means r choose k equal to r by k into r minus 1 into k minus 1, and this works all integers k not equal to 0, and there is no restriction on r. So, I will repeat once again. Yeah, we want to show that r choose k we want to show that r choose k equal to r by k into r minus 1 choose k minus 1. We will not have any restriction on r. This formula is always correct, whichever is the r. K also we do not have any restriction, except that we are not allowed to divide by 0, right. So, k not equal to 0 is required. See, k has to be an integer of course, otherwise the binomial coefficients are not defined. So, k not equal to 0, k is an integer, no restriction on r. So, what is this formula doing? R choose k is equal to, if we are converting it to r minus 1 choose r minus k, but what is coming out is r by k. This is what I say. This is easily proved, of course, there is nothing difficult about it. So, this is because r choose k, as we have seen, is r k following factorial divided by k factorial, and this is what r into r k minus 1 following factorial divided by k into k minus 1 factorial, which is r by k into r minus 1 choose k minus 1 by definition, right. By definition. So, the only thing is, or maybe you have to worry about when k equal to 0, what will happen. So, k equal to 0 was the only case where this factorial interpretation, this for instance this was rewritten as this, right. So, this was not correct when the lower index became negative, because see upper index was working for all k greater than equal to 0, right. So, if k greater than equal to 0, this was correct, right. And then for instance, if suddenly k minus 1 became negative, right. So, then the entire thing was not making sense, but k equal to 0 case we are not considering. So, therefore, there is no such issue, and if k was negative, we do not need this proof at all, because this is 0. So, whatever we are trying to prove, this is 0 and this is also 0, because k is negative, k minus 1 is also negative, both sides are negative, right. Sorry, both sides are 0, r choose a negative number, r minus 1 choose a negative number, both sides are 0. So, therefore, we do not have, we are, it is trivially true, otherwise we just have to use this, right, write it as r k following factorial by k factorial. So, now separate out r and k, and here k is not equal to 0, the k minus 1 factorial is still defined therefore, right. This is also defined because k is number which is bigger than 0, okay, right. Therefore, k minus 1 is there. So, therefore, we can reinterpret it like this. So, therefore, that is why it is correct. So, therefore, it works in all cases except when k equal to 0. Suppose we want to make it work for k equal to 0 also, what we can do is we can rearrange it as k into r choose k is equal to r into r minus 1 choose k minus 1. Now, there is no restriction for every integer k it works, because the only case it was not working was when k equal to 0. Now, if k equal to 0, this becomes 0 and this k minus 1 will become a negative number, and therefore, this will become 0, right, both will become 0. So, therefore, that absorption identity works for all k. Now, yeah. Now, what we are going to do is another one, namely some companion for this, in the sense that we in the previous case what we did is r choose k, like by pulling out something, namely r by k, we converted it to r minus 1 choose k minus 1, both upper index and lower index was reduced by 1. Now, we keep the lower index intact. R choose k we want to change to r minus 1 choose k, that only the upper index reduces by 1. So, the difference is that now it was k into r choose k is equal to r into r minus 1 choose k minus 1. Here instead of k we used that the remaining part r minus k. So, r minus k into r choose k is equal to r into r minus 1 choose k. This also works for all integers k, right. So, there is no restriction on r and there is no restriction on k, because the restriction on k in the earlier case was also coming only because we wrote it in the ratio form, r by k form. That is why r by k, because we cannot divide by 0, that is why we had to say k not equal to 0. Now, in this case we are writing like this, so we do not have a problem for all the or even any case, right. So, okay, so right. So, yeah, we will not have any restriction on any case r equal to k, or even when r equal to k equal to r we do not have a problem. See r equal to r an integer, right, k equal to r and k and r an integer, even in that case we will not have any problem. So, because you may wonder what if it becomes. So, we will show that this is true, but we will do it in the next class, but how we will do is by using the previous identity and symmetry identity.